So the outline for today is what is precipitation, at least from an engineering, the civil engineer or environmental engineer's context. And then we'll look at a property called intensity, duration, frequency. We'll investigate NOAA Atlas 14, which would be a tool that you would access if you're doing a hydrologic study outside of Texas and outside of the Pacific Northwest. The reason being is those two areas of the country are not in NOAA Atlas 14 yet. There's a whole who pays for what issue is why it's not there. What we have for Texas is an alternative called EBD Lookup 2015 or the Texas DDF Atlas, and I'll show you representatives of both. And then once we have a point precipitation depth estimate, then we can redistribute that depth in time by a couple of different types of design storms, and we'll get into that as we proceed. Okay, so precipitation, if you remember this diagram, we've seen it before because I made it once and I wanted to get as much miles out of it as I could. And we're focusing in that rose-colored ellipse, like rose-colored glasses, only different. And that's the precipitation. So that's what today's discussion is about, is that rose-colored ellipse, this thing right up here. Okay, unlike flood frequency, which we were temporarily done with, there's precipitation comes in more than just what's the rate right now. It has four variables of engineering interest. The first is intensity. How hard is it raining? The second is duration. How long does it rain at any given intensity? The third is frequency. Think of that as a probability. How often does it rain at any intensity and particular duration? And then the fourth, which is the last part of today, is spatial distribution. Excuse me. Yeah, it's not last part of today. It's spatial distribution, how it's spatially distributed over an area. Clearly, if the area is a parking lot, standing in one corner or the other corner of the parking lot and it rains, you're going to get just as wet. But if that area, on the other hand, is the 600 some odd square miles that Lubbock County comprises, being in one corner of the county might be pretty beneficial if you're trying to stay dry. So that's what's meant by spatial distribution. Okay, unlike flood frequency, the rainfall probabilities are expressed in a combination of frequency, depth, and duration. Frequency and rainfall frequency is the same concept as annual exceedance probability. So a 10% chance rain or a 10-year rainfall event has the same probabilistic context. But what differs is a 10% chance storm could come all at once in a couple of minutes, or it could be spread out over a long period of time, and those storms are going to behave differently, yet have the same probability. So we always, with rainfall, we're always talking about the duration part too, how long it's happening. Including depth and duration reflects things that you may have personally experienced, is that two different storms can produce the same depth but delivered over much different time. Imagine a slow, gentle rain for a long time. You don't have to like strip your clothes off and put them in a Ziploc bag and run around in your surf shorts and then put it back on when it stops raining, versus when all that rain comes at once, usually as you're fussing with your key on your car and you're in grown-up clothes, boom, instantly soaking wet. The Ziploc baggie thing, I lived and worked in Hawaii many, many, many summers ago, and that's how we handled rainstorms in Hawaii. Because basically it rains about 4 o'clock every afternoon for 25 minutes, and you just took your clothes off, stuck it in the bag. We kept our pants on. And then when it was done, you put it back on and went on about your thing. I was working on a dive boat. We were stuffing, quote, corn-fed Iowans into wetsuits, strapping tanks on them, stuffing the thing in their mouth, and pushing them overboard. Because that was 35 minutes of peace until they ran out of air and came back up for more. So it was good work a long time ago. Probably they don't let you do that anymore. It probably got rules and stuff. But at the time, there weren't. As long as we didn't kill them and they paid cash, it's good to go. Okay, depth, duration, frequency. The depth of the rainfall is how much rainfall, or think precipitation. I'm using rainfall and precipitation interchangeably in this talk. Mostly because rain is what we usually have to deal with a lot in Texas. Yeah, it snows here, but not a lot of months a year. The depth of rainfall is the accumulated depth over some time interval. So that's how much rain is caught in a gauge. Think back to our garbage can watershed representative. Now that garbage can represents a rain gauge. So if an hour goes by and we get 3 inches in the bottom of that rain gauge, we would say we captured 3 inches for that hour. Another hour goes by, 1 more inch comes in. What's the cumulative depth? It's 4. So we get 4 inches in 2 hours, and so on. Duration is the time interval, that 1 hour, that 2 hour, that 3 hour, whatever the capture time is. And then frequency is the probability of observing that depth over a given duration. So we ask, the frequency question is, what's the likelihood or the probability that we will catch 4 inches in 2 hours in our trash can? And that would depend on what the rainfall behavior is for that location. And this information is presented back to us in something that's often called a depth duration frequency curve. Let's see. Yeah, I had that done as in depth. Or an intensity duration frequency curve. The difference between depth duration frequency and intensity duration frequency is simply the first word. Each one contains the information of the other one. The intensity would be that. I'll have a picture of it in a minute. Okay, so this is a picture of a depth duration frequency curve for somewhere. And this curve right here that I'm following is representing a 100-year annual recurrence interval. And then this curve up here is a 1,000 year. Now 1,000 years is ridiculous. We never see that on real depth duration frequency curves. It's of practical use. We don't care about a 1,000-year rainfall. That is so improbable that I would be willing to sign your name on it and use your engineering stamp and not even look at the plans. Not a good idea, but we don't worry about that in our work very well, probably never. 500-year does come up from time to time in water resources engineering, mostly for things like building dams just upstream of expensive subdivisions. All the big dams in Austin are supposedly been studied for 500-year events. It's still real cool when houses go over their spillway in Marble Falls. That's just great video. I'd hate to be in the house. Okay, so normally the DDF curves are presented as a family of curves. So there'll be a curve associated with a 2-year, 5-year, 10, 20, 50, 100, and maybe 250 and maybe 500. The horizontal axis almost always by convention is time, that duration. How long does the rain occur? And the vertical axis is almost always, by convention, either the depth, if it's a DDF curve, or the intensity, inches per hour, if it's an intensity duration frequency curve. And so for this picture up here, for example, the 12-hour, 100-year depth, we go to 12 hours duration, we read up to the 100-year line, move horizontal, and we read a depth of, well, it says, yeah, 70 millimeters. A little bit less than half the distance between 50 and 100, so 70 millimeters. And that is a depth duration frequency curve. Let's suppose I was to ask you all the question, what is the depth for a 4-hour duration, 100-year rainfall according to this curve? Your best eyeball guess. 50 millimeters. Excellent. Good. If I had a stuffed animal, you don't want it. Okay. Intensity. An alternative to depth, duration, frequency is to present the magnitude as an intensity, as a rate. And again, both are used in practice. There's no special advantage to one over the other. It's dependent on the jurisdiction and what people are used to. Intensity does have an advantage for something else, but not today. Intensity is the ratio of an accumulated depth to some averaging time. And usually that averaging time is the duration. Here I've selected the letter of the alphabet, capital T, lowercase c, not because it's the initials of my names, although that's kind of cool. It's supposed to represent time of concentration, which is a certain kind of averaging time that's used a lot in certain hydrology. So it makes sense to just keep it up there. But for the time being, for this discussion, the T sub c is just an averaging time. So if the depth was 70 millimeters, and the averaging time was 12 hours, if we want to express that as millimeters per hour, what do? We take the 70, divide by 12. So there's 12 times 5. There's 5 point something millimeters per hour represented by the 70 millimeters in 12 hours. Okay, that would be called the average intensity. Intensity, as shown here, is not the instantaneous rainfall rate. Under what conditions would that statement be negated? In other words, when would intensity, as shown here, be the same as the instantaneous rainfall rate? Calculus question. It would be when the time of concentration is approaching 0. It would be whatever the limit of that thing is as t approaches 0. Okay, so here's the intensity-depth relationship, and this is me taking a cop-out using the same curve. But if we recast the vertical axis, that left axis, and instead of having it record depths, have it report intensities, these intensity averages, then where the 70 appears on it right now would be replaced by 5.8. To represent 5.8 millimeters per hour is the intensity associated with a 12-hour, 100-year event. Okay, we don't usually plot intensity curves to look like that. Instead, they get plotted to look like this. I'm going to try something I might regret, but just once, I want the curves to line up the way they're supposed to. Better. Okay. Intensity, duration, frequency curves tend to look like this. They're big at the left end, and they I have these ones swooping down, but they're concave like a bucket. More often they move across and then down. That part's irrelevant. The shape is irrelevant. They have big at the left end, small at the right end. So for example, the family of curves is shown here, 2, 5, 10, 25, 50, 100. Those represent annual recurrence intervals, 2-year, 5-year, 10-year, or the reciprocal of those is the percentile, annual exceedance percentile. And then the left axis is the intensity in inches per hour, at least as shown here. And the horizontal axis is duration, in this case in minutes. And so the 20-minute, 5-year intensity is 5.5 inches per hour after I've moved my lines around a little bit to where they're supposed to be. Okay, so this family of curves, this is the one that's depicting intensity, duration, and frequency. And it's a fundamental part of the rational equation method, which is used for really small watershed infrastructure design, and a reasonably important part of other hydrologic methods that are used for stormwater drainage. Okay, were that you were forced to, how would you construct an IDF curve? Well, there's a handful of ways. The easiest by far is to look at your neighbor's one and hope they got it done before you, but that won't work in this class. Instead, we would get the depth, duration, frequency information from maps of depth for a given duration. And there's such maps available from a few places. There's a product from the National Weather Service called TP40. It's originally from the 1960s. It's been updated a couple times. And what it is a map of the United States with an annual recurrence interval on it and a duration, and then it represents the contours on the map represent rainfall depths. I don't have a picture of it here, but we can go out and look at it later on. Second one is HY35, also by the National Weather Service, and it works for the eastern United States. Just take a line in the United States, go to the left edge of Texas, go north, throw out all that west coast stuff, and everything to the east is in HY35. And it's also for shorter durations than TP40. Okay, a newer product called NOAA Atlas 14 is online, and you just click on a site and it gives you the DDF data for you. We might actually try that live. And then, of course, since Texas is not part of NOAA Atlas 14, we have a Texas DDF Atlas, which is also online, or you could download the actual USGS product. And actually, I think the USGS product is in the readings on the website, so you don't even have to go find it. Okay, here's what any of these products having it glued is a pain in the... Yeah, nice try. They all convey pretty much information in the same fashion. Each one's a little different, but you'll be able to figure it out pretty quickly by context. Bless you. So this is the United State of Texas. And there's a map, and the map in this case shows the counties. And then these contour lines represent depth of precipitation. Okay, so this contour line right here represents 2.2 inches depth. Pretty much going through, well, down here is like nowhere, Texas, and here is somewhere Lubbock. The other piece of information that the maps convey is a probability or an annual recurrence interval. In this particular instance, it's done an annual recurrence interval. So this is depth of precipitation for 5-year storm for a 3-hour duration. So we have probability, duration, finally you have location, which is the whole point of the map. And then once you know your location of interest, you can interpret the contour lines. And in this example right here, so the Harris County 3-hour, 5-year depth is 3.6 inches, and this is the 3.5 line. That must be, I can't read, well, I can't possibly see it here either. Anyway, I've interpreted these three contours. This one that goes right through the Harris County is probably what I used. It's 3.6 inches of depth. Okay, so if you're from Bexar County, San Antonio, it's over in here somewhere, you have a different depth associated with a 3-hour, 5-year storm. Okay, there's 96 of these maps in the Texas product. So if you have the paper one, finding them is a pain in the neck, but I'll show you a cool way to do that. But as long as everything's working, it's great. And if not, you have to load it. You have to download it and interpret it. Let's suppose you had a reason to build an intensity, duration, frequency curve for a location. Now, for a one-of kind of project, this will be a waste of time. But if you're working in Bexar County over and over again, at some point it's going to get tired to go flipping through those maps every time. So I'm going to build myself my own IDF curve and be happy with it. So you select the annual exceedance probability of interest. You locate maps for that AEP for each duration of interest. From each map, write the duration and depth into a table for the location of interest. Plot of the depth versus duration for the tabulated values is a depth duration curve for that particular exceedance probability. And then if you need intensity, you just divide the depth by the duration. The result is depth per duration, which is intensity. Repeat as needed for different AEPs to construct a family of IDF curves. That looks almost like the algorithm that's on a bottle of shampoo. What's it say? Lather, rinse, repeat. But it never tells you when to stop, does it? So always buy little bottles of shampoo. You don't waste as much money that way, because when it's empty, you can stop washing your hair. Okay. I always thought that was funny. Get some courtesy laughs. Thank you for the courtesy laughers, and curse the rest of you.
There was a Pinky and the Brain episode where Brain's idea to take over the world involved making everybody shampoo themselves over and over and over and over and over again.
I've never seen that. So I arrived at that all by myself, no help. That's actually kind of pathetic. Huh. Okay. Let's suppose we want to build an IDF for Harris County. So just following the list of shampooing over and over and over again until you're cleansed of all your sins. I could do preaching up here if I wanted to. You construct the IDF curve for a 50% chance storm using the DDF Atlas. So step one, select the AEP. It's been done for us. We want the 2-year storm. Step two, locate maps for the 2-year storm. If you go to that particular document that I had the cover of, those are figures 4 through 15 in the Atlas. Step three, from each map, write the duration and the depth onto a table. Next 2 slides will illustrate looking at the maps and gathering that information. Then step 4 is divide the depths by the duration to obtain an average rate. Okay, so here we go. We've done step 1, and for all practical purposes, just pretend you've done step 2. So we're going to look at steps 3 and 4. Okay, so laser. 15-minute, Harris County, 1.1 inches. Write it down. I mean, not in your notes. Not being. You would write it down in order to put it into a table. 30-minute, Harris County, 1.5 inches. You would record that, and you repeat that for all the different maps associated with what you're interested in. And finally, you'd have this very exotic table, extremely. I mean, this is really high-level science, and you could go to the moon with it. The duration, in this case in hours for plotting, the depth that you wrote down, and then this last column is that depth divided by that duration. This one is that depth divided by that, all the way down. And so we have intensity as a function of duration. And so a plot of that column and that column would be an intensity, duration, frequency curve for Harris County for a 50% chance storm over durations ranging from 15 minutes to 7 days. Yeah, 7 days. I think that's 7. And if you plotted it, it would look something like this. Now, this stuff, much past 24 hours, isn't going to be terribly interesting for most engineering stuff at the scale that we're ever going to be involved with. We're going to be building parking lots and Walmarts, and maybe if we're lucky, a few miles of highway. We're not going to be necessarily having a big deal to worry about them 7-year storms, but some of you will get jobs with LCRA, Colorado River Authority, and big stuff, and then you'll care about the later times, but the rest of you won't. But we don't know who that is, so you all have to be able to be cognizant of it. So that's that just taken from the DDF maps. Okay, so you can get the maps yourself, or there is a direct web interface for it. Yay. Okay, so that link takes you to this web page, and so we can pick any of those. Are those annual exceedance probabilities or annual recurrence intervals? Annual recurrence intervals. Good. You saved the rest of your classmates from taking a quiz. Mwah, evil laugh. Let's pick 25 year just for grins. So 25-year annual recurrence interval. Choose a duration. Let's do 25-year, 1 hour. And if it's functioning right, boom, it goes out to the who's in my what's it, grabs the map. And this actually works faster if you're not on Texas Tech campus. Okay, so all it did, it has a copy of the map out of that atlas, and it just grabs the particular copy. And that's a lot faster for me. So I wrote this for my own use. I mean, I'm just sharing it with you out of the kindness of my heart because I pay me to. For when I have to do my Texas stuff, because I got sick and tired of flipping through the book or having to download the book every time. Somebody pick a county that I can find. Okay, Lubbock County is up in here somewhere. And so the 25-year, 1 hour storm depth for Lubbock County is somewhere in the 2.6 inch range. Okay, what would be the 25-year, 1 hour intensity for Lubbock County? Come on, that's arithmetic you can do in your head. 2.6 inches divided by 1 hour is 2.6 inches per hour. So that is an example of that tool. The alternative is you can actually go to the actual report. Oh, I'm going to regret doing that. It's going to take forever. It's going to download a report that's going to take to the end of all of our lives combined. There's something wrong with the network on campus, so I can upload stuff to the rest of the planet practically instantly. But I can't download anything to save my life. That's just been the last few days. So I think they hit a fiber optic cable with a backhoe, and they just spliced it together with some clear epoxy, and it's sort of working, but it's not sort of working very good. Okay, well when it loads, I'll show it to you. It's just a report. Okay, we will now look at the static content. So this is a static example, what I just did live. Go to the direct access, you enter annual recurrence interval, a duration, hit submit, it brings you a map. Then you have to use the map in the usual way, draw a circle on it and find what you're looking for. Alternatively, you can download the actual report, which my thing will do whenever it feels like it. And that constitutes the tools that are available for Texas for depth, duration, frequency. Okay, now if you're not in Texas, downloading the Texas map is pretty useless. Instead, you would want to access this tool, which is called NOAA Atlas 14. And NOAA Atlas 14 is actually the name of the physical paper document. We're actually going to go to a Point Precipitation Federal Data Server. That's what that PFDS means. Precipitation Frequency Data Server. And so it's interchangeably used with NOAA Atlas 14, although they're actually different things. The Atlas, or the server here, is an online tool that returns tables of depth for a given geographic location. And there's what it's called, and there's the link to it. I'll go to the real link in a second. The blue states are states that are currently in the precipitation data server, the dark blue states. The light blue states are one whose political affiliation is undecided this next election. No, just kidding. They're the ones that are supposed to be included in the data server in the next few years. Now, an interesting point, National Weather Service and NOAA has said they were going to incorporate Texas in it for my entire career, and I started teaching in 1990. So the next few years is just sort of who knows how long it could be. That's why the Texas tools exist. My colleagues and I built them because it was clear that the feds were never going to get around to it in anybody's lifetime, and they needed the tools. The Pacific Northwest is currently not in it, but I bet you they'll be in it before Texas. And then the Northeast part, there's older stuff in it, and that's like New York and stuff, and they need to keep jacking with it so they can keep getting all that federal money every time a little storm comes and, you know, knocks the crown off the Statue of Liberty, and they want to get $55 billion to put the crown back on. It's like, it's 20 minutes in a helicopter, boom, that's $2,000 airlift time. So I don't know what they're doing with the other billions. Probably buying mint juleps and having parties down on the Madison Square Garden there. Okay. If you go to NOAA Atlas 14, you get a map. You can zoom in on a place of interest. I have no idea why I was interested in Oklahoma City when I made this, but Oklahoma is okay. And very similar to the Texas Online tool, although it's got prettier graphics. You would select a location. So this is the crosshair. You tell it whether you want a partial duration or annual duration series. All I've been talking about in this class is annual duration series. Partial durations are related, but they're a different thing. And then it'll return a latitude and longitude, and then when you have it produce the chart, it produces a chart like this. And the moving down a column is increasing time. Moving across the table in a row is decreasing probability. Okay. Be very careful when you get to pictures like this that it doesn't have a destroy button. You know that if you do, you're on the Department of Defense server, and it can make cities disappear. Just kidding. They wish they had that. The Air Force does, but they never get authorized to use it. And let me go try it live. One more time. Okay, wait for it. Famous Lake Skunk Depew. Okay, so here is the server quasi-live. Let's pick Oklahoma because it's okay. You get the irony of that, right? You've seen the license plates? Yeah, okay. Ha! It's processing. Please wait. The server has detected you've moved your mouse. Would you like to reboot now? No. I don't dare move that red crosshair once it comes through. I mean, just stick with whatever it gives me and call it good. The processing part is happening not because of their end. It's because of Texas Tech's end. For whatever reason today, the bandwidth coming on the campus is minuscule. It's slightly faster than dial-up, although you wouldn't know it right now. And I would dare say many of you were pretty young when dial-up was a big deal. Okay, I am going to let it do all this stuff in the background and keep going. And we'll take a look at it in a minute when it comes back to life. Okay, so those were depth, duration, frequency. In Texas, we have another tool, actually brand new, called EBD Lookup. And what it does is it uses that depth, duration, frequency information to fit values to this equation. And then this timing term can be arbitrary. It doesn't have to be 15 minutes, 30, 1 hour, and so forth. And the E, the B, and the D refer to the coefficients in this power law model. So I is the intensity inches per hour, T sub C is the time of concentration in minutes, B is some scaling value, D is an offset in minutes, and E is an exponent. And so the values of B, D, and E vary by county in Texas. And so how that was arrived upon is those depth, duration, frequency maps were made on a database of a gazillion letters of the alphabet in it. 68,000 and some change data points. A surface is passed through all those data points, and an equation is extracted from that surface for each county. So just like you did in your introduction to computing programming class, and you fit straight lines through data, we'll just imagine that in 1, 2, 3 by 254, 3 times 254 dimensional space. Okay, it's just been a bunch of big numbers. It's just passing a curve through data. It's a little more sophisticated than that, but essentially that's the concept. And when it's done, you have the ability to estimate an intensity by county for any arbitrary time of interest. Well, not completely any. It doesn't work for negative times, and you go much more than 24 hours, and it was never fit because the designers of the software decided that 24 hours was plenty. And if you were worried about bigger times than that, you were not doing ordinary infrastructure design. You're doing something else. Okay. So converting between intensity and depth is pretty trivial. Intensity is obtained from depth by dividing by the averaging time. Conversely, depth can be inferred from intensity by multiplying by the average time. That's assuming that the durations are the same. Okay, let's see if my NOAA Atlas 14 is here yet. Are we here? Yeah, you're going to just take it on faith it works. I'll save that for a minute. Go away. All right, on the off chance that it's a web server issue, this may have no difference whatsoever. Yeah, it doesn't look like it's going to make a bit of difference. Oh, that was faster than I expected. I'm doing this for a reason. I'm actually going to want to be here in a second. Oh, come on. Okay, the EBD lookup tool I'm about to discuss is on the web server. It's in a pre-release form because at the time it was put up there, it hasn't been officially released yet. As far as I know, the Texas Department of Transportation is trying to figure out where to put it, but it exists. It's a real thing, so you could use it for work and actually use it. Okay, I think I don't dare with the website. I'm pretty sure I have a local copy of it. Okay, I do. So I'll go back to the presentation, but I'll be coming back to this local copy in a second. Okay, so the purpose of that tool is to create a design storm. Let me actually illustrate. Okay, let me illustrate the EBD lookup real quick. All right. Yeah, that more or less fits on the stream. Okay, so it's a spreadsheet interface, and what you can't see is there's 3 other spreadsheets hidden behind here. Okay, one other spreadsheet hidden behind here. Here's the database of E, B, and D values by the different counties in Texas. And you could actually access those directly and write your own equation if you wanted to. It should throw an error message. It's write protected on purpose. When you get if you ever get the report, it tells you how to defeat the spreadsheet security. Defeating Excel security is pretty easy. For a small fee, I could show you right now, but I won't. Not that I'm that worried about it, but it's really easy to do. It was built into the Excel program to prevent you from breaking stuff that you got working. It was never meant to keep stuff secret. So when you leave here and you work for a big insurance company, you have customer data on a spreadsheet. Yeah, by all means protect it, because the hackers won't ever be able to get to it. That was cynicism. I hope you got that. Okay, good. So here's how the spreadsheet works. It's fairly simple. You choose whether it's going to be English or SI units. Let's do it in English because that's the only language I speak. Whereas C is yes. C, yes.
Oh.
Yeah, duh.
C.
Da. And then you would choose a county. Possibly in my lifetime. There we go. You have to click into the blue box. And then we can choose a county. Currently it has Calhoun County, which is somewhere between Houston and Victoria on Highway 59. I know that because I've driven by it many times, but let's pick a different county. What county do you want today?
Rockwall County.
Who?
Rockwall County.
Rockwall. That begins with an R, H-I-J-K, L-M-N-O-P. You don't have to necessarily do pull-down menu. Red River, Reeves, Refugio, Robertson, Rockwall it is. Okay. Then we have to pick a rainfall averaging time that we're interested in. We're not stuck with the 15-minute, 31 hour of the maps anymore. Okay, so what's the mean attention span of anybody in this room at almost 3 in the afternoon? I'm thinking about 11 minutes. Let's do 44. That's just a weird number, right? Between 30 and an hour. It's definitely not mapped. They'd never map that oddball of a number. And then we decide whether we want it in minutes or hours. I think we'll stick with minutes. And ta-da! So what it did is it went out to the database and it pulled the E, B, and D values for the 2-year, 5, 10, 25, 50, and 100. And then it applied that equation, intensity equals B divided by T sub C minus, no, T sub C plus D, quantity raised to the power E, and reports back an intensity. So 2-year, 2.7 inches an hour, 100-year, 4.82 inches an hour. And we can switch to units of hours. So a former student of mine did this as part of their master's thesis thing. Okay, so this is a tool, and this replaces an older one called ABD lookup. This is about as close to no brains required as they can possibly make in hydrology. The only thing to make it easier if it was just a single button, a big green button that you press to go ahead and bring maps up. This is 3 things. Well, 4 if you count the units. Okay, not too difficult to use, but if, for example, on your semester project, it's going to be in a place called Concho County, home with the famous rodeo cowboy Concho Billy. Oh, y'all, way too young for that. That's hilarious. Okay. And there's the 1 hour for Concho County. So you guys got 17 square miles of drainage area. 4 times 4. That's about a 4 hour concentration time. You would expect for 50-year annual recurrence interval, which might be the annual recurrence interval you end up selecting for your structure, about 1 inch an hour for 4 hours. So what's the total catch? Quiz question. 4 inches and some change. Well, actually, almost 4.5 inches, because 0.14 4 times gets pretty close to 5 and then some. Okay. Back to that. All right, so once we can estimate the intensity, that's good. But sometimes we're also interested in how that storm behaves as time progresses. So that 4 inches over 4 hours, do we really expect it to be 1 inch an hour for 4 hours? Or is it maybe like 3 inches an hour for 10 minutes and then whatever the rest is dribbling along? And the answer is yes, it is something different than what we expect. When the time behavior of a storm is important, we have to use something called a design storm. It's more of a concept than it is a thing, and we need to generate hyedographs. A hyeidograph is simply a time series of rainfall. So as time progresses, it's either the accumulative or the incremental as time progresses. It's called a hyeidograph, coming from the word Hyatt, which is part of the Hyatt Regency Hotel chain, for which I get a kickback. I think it's a Greek or some sort of oddball word for rain. Okay. Design storms are themselves just statistical models of temporal behavior, and they're used in hydrologic models when we have to generate a hydrograph. Okay, so if we have a situation where we need a hydrograph, an estimate of discharge at a location versus time, we're going to be forced, at least in rainfall runoff calculations, to have to use a hyeidograph to generate that hydrograph. There's an alternative thing for really small things. For parking lots, we use the rational method. All it does is estimate a peak discharge. Makes no contention on when that peak's going to occur, if that peak's going to occur, why that peak's going to occur. Then in that case, all we care about is average intensity, area, and some other things. But when we want to generate a hydrograph, we would use a design storm. Okay, so rainfall distributions themselves, they represent time patterns of a storm. And they're statistical representations. There's no anticipation that a design storm is going to look at all like a real storm in a realization sense, but they share the same statistical characteristics of a real storm. The rainfall distribution is also called a hyeidograph, and it's used when we need to generate an entire hydrograph. Okay, this is a graphic you've seen before, mostly to associate cumulative and incremental because it's a big deal in rainfall. So the rainfall is collected on the blue line. Rain gauges all work on cumulative. And the reason being, it's actually an instrumentation requirement because it's far easier to build an instrument that every time 1/100th of an inch of rain comes in, it sends a signal. Rather than having it poll, P-O-L-L, have a computer poll that instrument every second, it's easier to just, anytime something happens, you send the signal and then you post-process it. Post-processing is big fancy mumbo-jumbo for taking the blue line and making the red ones out of it. So you would, we difference it. The distributions get created from historical storms. They're analyzed to make statistical models of rainfall. These models are called design storms. That's all a design storm is. It's a statistical model of rainfall for some location. They're almost usually presented as dimensionless hyedographs. And the two in common use, or that we're going to discuss, or at least see, one's the NRCS type storm, and it happens to be built in a HEC HMS, so it's good to at least see where that comes from. And then the second one I'm going to present is the empirical Texas hyetograph. And it's based on some work by Huff up in Indiana. In your team design class, I think you need to do a first quartile Huff storm. I don't even talk about them, but if you read the document on this guy, it refers back to that one. I'll try to allude to what they are when we get there. And you can read about the NRCS type storm in Chow, Maidment, and Mage on pages XXXX through XXX. I didn't have the page numbers yet. For what it's worth, actually, the Chow, Maidment, and Maze is probably one of the better descriptions of what a design storm is of any book you could get, even stuff that was written recently that uses colorful pictures and things. Okay, so the SCS type curves. In the 1970s, the Soil Conservation Service, currently known as Natural Resource Conservation Service, no telling what it's going to rename itself in a few years, analyzed depth, duration, frequency curves to develop a dimensionless rainfall pattern called type curves for 4 different regions of the United States. And it covers all the United States. They're in the form of something called a percentage mass, or a cumulative curve. And the key thing about them that's important is their time base is 24 hours. They're for 24-hour rainfall. A lot of documentation will refer to ways to pick different durations. I think the safest bet for y'all is to just assume it's flat out wrong. There are 6-hour NRCS or SCS curves available, and I have that copied on in this lecture and on our server. But other than those two, other than 24 and 6, any other time duration with SCS is a joke. That's just safe. It was originally built to be used with SCS curve number runoff generation model. So what we're going to end up doing in this class, we're going to break it apart and reassemble it, but it was never meant to be done like that. The SCS type curve is supposed to be used with SCS runoff curve, SCS curve number procedure. They're not supposed to be broken. Historically, they have been. There's no super big damage in doing that. Your depths will still come out right because you don't parameterize them by SCS data. You use National Weather Service. The location where you are in the US of A selects the type curve. Now, if you happen to be like right here in Ciudad Juarez, nothing works. No, it's right there next to Texas. You'd probably be okay using the type 2. So all this yellow stuff is type 2. The light brown is the Pacific Northwest coming down in California. The dark brown is Southern California, Alaska, and Hawaii. This gray shaded area under the curve is the Atlantic seacoast. It's part of Florida that was intended to be washed off the planet by hurricanes, but hasn't happened yet, so they located Cape Canaveral there. And this central part of the Gulf states. Okay, Texas is special because it's so big that it has 2 type curves associated with it. That green line, for all practical purposes, is Interstate 35. If you're to the left of it, to the west of it, you use type 2, and if you're to the east of it, you use, anybody? Type 3. Okay, and then the curves themselves, they plot like this. I'm having fun with the laser. There's the type 2 curve. There's the type 3 curve. Nice safety feature built in. If you screw up in Texas, it's probably not that big of a deal because except right in there, type 2 and type 3 are tracing the same thing. And let's suppose in a 24-hour period, for some location, the total catch is 10 inches. So we start at midnight, and we go to midnight the next day. And the end of the next day, we look in our bucket, and we've got 10 inches of rain. So what this type curve is saying, well, The way that bucket filled up was at midnight, nothing much interesting was happening. And then it rained a little bit until about noon, and then it went ka-whoomp and filled up with water almost instantly, and then rained a little bit to get back to the 10 inches. So most of the interesting behavior happens in the middle of this distribution. And it's a centered storm. It happens at the 12th hour. Not the 11th hour, which is when homework gets done, but at the 12th hour when it gets handed in. The type 1 and 1A, they have their steep part a little earlier in time. And here's what the distributions look like in tabular format. So type 1, 1A, 2, 3. This is the hour. So hour 0, 2, 4, 6. And then this is the fraction of the 24 hours that's associated with a particular hour. So at hour 12 is half the storm. At hour 20 is 83%, and at hour 24 is 100%. What I want to call your attention to any the SCS type storms, if you're using tabulations, you take them off the internet. I don't know where else you get them. They have portions where they're not uniformly spaced in time. So hour 2, 4, 6, 7, 8, 8.5, 9, 9.5, 9, 7, 5, 10, 10.5, 11, 11.5, 11.75, 12, 12.5, 13.6, 13.5. It's that new math. That's got to be an error, and so on. The point that I'm trying to make there is the NRCS, they're not uniformly spaced in time. So the exercise you just got back where you had to insert time spaces, I didn't pull that out of my datum entirely. There was a reason why I had you do that once in your life, because this probably might be the second time. Not for this class, but sometime in your future. The 6-hour one pretty much has the same structure of time, fraction of total depth, and the ratio of the fractional depth to the total depth. And those ones aren't uniformly spaced in time, but I don't have that bizarre time counting right there. Both these distributions are taken out of the Chow, Maidment, and Mays book on page XXX to XXX, wherever that is. So you can correct that one error I have. How we would use them. Okay, so to use them, use the DDF Atlas, TP40, whatever. Set total depth for the 24-hour storm or for the 6-hour storm if that's what you're interested in. Choose an appropriate SCS type curve. That depends on where you are in Texas. So if you're left of 35, you choose type 2, and if you're right of 35, you choose type 3. Good. You rescale the type curve with capital P, which in this case is total rainfall depth, to get the design mass curve, and then if you need it, you can pull the incremental precipitation from the rescaled mass curve by differencing between two time units. Here's an example. Suppose we're asked to generate a design hyetograph for 25-year, 24-hour duration SCS Type 2 storm in Harris County using 1-hour time increments. So we'd look up the 24-hour, 25-year depth for Harris County in DDF Atlas. The cumulative fraction we would interpolate in the SCS table. Cumulative rainfall is the product of the cumulative fraction times the total 24-hour rainfall. The 10.01 inches is the number we're going to come up with when we look at the map. And then the incremental rainfall is the difference between the current and the preceding cumulative, and then you can plot the results. So look up the 24-hour, 25-year depth for Harris County. This is going to get, this probably should be getting old for you now. Depth of precipitation, 25-year, 24-hour, which is the same as 1 day. County of interest is right there, and the total depth is about 10 inches. I believe I used 10.01 in my calculations. Okay, and then use the SCS tabulation. So this has the hours. Now it's convenient here, somebody's gone to the trouble to take those oddball increments out. That'd be neat. And the cumulative fraction. associated with that time history. This number here, this is, excuse me, this number here is that total depth, 10.01 inches multiplied by that fraction. So 10.01 times 0 is my favorite number of multiplication because you get 0 back, no brains required. And moving on out till we get down here to the total depth of 10 inches. These values are the increments. It's that value minus that value divided by that value minus that value. So it's the amount that was accumulated at the beginning of the time step. So at the beginning of the storm, at time 0, at the beginning, we've accumulated 0. At hour 1, we've accumulated 0.1 inches. At the beginning of hour 2, 0.2 inches. At the beginning of hour 3, and so on. I just noticed I have a mistake in this chart. So if you're taking notes, just write to yourself that the right column should shift up 1. So this number should be up there, all the other ones shift up, and that 0 comes back down to the end. My bad. And then when you plot it, you get the blue hyetograph right here. And these represent incremental depths for a 1-hour increment, hence they happen to also be equivalent to 1-hour rainfall rates. And so hour 12 and hour 13, as I've plotted it, which really should be 11 and 12 if it shifts to the left like it's supposed to, I have roughly, each of them is producing 2.5 inches of depth for their respective hours. So 5 of the 10 inches happens in a 2-hour period out of this 24-hour storm. And then the remainder is captured before and after that. And you notice that storm is centered about a peak, and that's called a centered storm. And that's one of many different storm designs that's used in design storms. Centered storms are pretty common and typical. Okay, so that's SCS. I think it's reasonably straightforward. Next one is Texas empirical hyetographs. Now this is an alternative to the SCS. Here's its wonderful features. One, it's based on Texas-only data, so that doesn't necessarily make it better. Secondly, all the storms in this document are known to have produced runoff. So not only did it rained and made water run off, and that's actually a big deal west of I-35, because it can rain a lot in Lubbock and water doesn't go anywhere except into the ground. So these are known runoff-producing storms. And what we observed when we studied these, wow, is that long ago, in the early 2000s, that there's a front-loading occurs in storms, and then the rescaling of time and depth will make sense in a second. Okay, so these are the statistical models of, I think that was 58,000. It's basically 6,000 storms at about 110 different locations in Texas. It's a lot. It's a lot of letters of the alphabet. And in Texas, a lot of storms have the feature that at time 0 it starts raining, and it rains hard. And then it kind of peters out and sort of dribbles on a little bit later, and then after a considerable amount of time, the rain's over. Now, the cause of that is probably the storm moving over an area. But we can't capture that point precipitation. Very rarely in the data in Texas do we see it sort of raining about the same for the entire storm, which would be this average intensity line. And even less common is for it to be, I'm not sure if I really want to rain. Yeah, maybe I'm going to rain some more. Yeah, I'm going to dump on you. Okay? The more likely behavior is somewhere between this magenta line and the 90th percentile. Let me explain what the percentiles mean in this chart, because they're different than percentiles and other stuff in the class so far. So 90% of the storms studied in this study, that's good English there, would plot along this trajectory or somewhere below it. 10% of the storms in the study would plot on this trajectory or somewhere down in this corner. So most of the information is bounded in this area. I'll do that, try to make you all dizzy and vomit. Okay, the laser's helpful. I'd probably be much better with putting vodka in the, but that's nasty. Up in here is pretty rare. We hardly ever see storms that go, bam, done. But it's possible. Okay, the magenta line is one of 2 recommended ones in that report that I showed you the cover of. This is the median storm. So half of the observed storms in the study plotted above that magenta line and half below. So the magenta line is kind of like an average or a typical one. And let's look what the typical one does. It rains hard for a little bit and then it's pretty boring. So hard and kind of but it's above the average intensity, which would be corner to corner, most of its entire life. Now, you might ask yourself, well, how can it be the average intensity? You got to both get to the same endpoint. Well, it's steep here, but it's shallower than the average one there. So that's how they end up back at the same endpoint. Okay, the way we would use this. Let's suppose we're going to use the 50 at the median storm. That would be a good one to use if you have no other information. You want to use this method. If you're really scared or your client's got a lot of money, use the 90th percentile one because you'll make something a lot bigger with the 90th percentile. If you know you're going to skip town and take your trailer with you and go to another state, well then use the 10 percentile because you won't care, right? You'll be gone. Let's say it's a 3-hour storm or a 5-hour storm. We get that 3-hour or 5-hour from the DDF Atlas. Or if it's an arbitrarily funny time, we can use the EBD Lookup 2015 spreadsheet. Anyway, we can get the time axis. Multiply the depth axis by the storm depth, also obtained in the same data source. And the result is a design storm for a given duration and a given annual exceedance probability, and it produces the cumulative storm. So let's do a quick example, or I'll do a quick example. You just pretend to pay attention and care. Construct a design storm for 3-hour, 2-year rainfall in Harris County using the empirical hadograph. So we could get the depth from the DDF Atlas and then rescale depth and time using the empirical hadograph. We'll do it graphically first, and then I'll show you the tools that alleviate you from having to draw pictures and photocopy stuff. So this time axis, which is currently a fraction of total time as plotted, 0 becomes 0 hours, 100% becomes 3 hours, 66.67 becomes 2 hours, and 33.334, and a bunch of other letters of the alphabet, numbers, becomes 1 hour. So this axis remaps from 0 to 3 hours instead of from 0 to 100%. The vertical axis remaps from 0 to 2.6 inches rather than 0 to 100%. So for an example, after 1 hour, come up to the 50th percentile line, we're about half the storm is done. We've got our first 1.3 inches in the first hour. We get the next 1.3 inches over the next 2 hours. So it's reflecting that it's steeper in the first hour and less steep in the next 2. Okay, it's clear. It should be clear to you that if I wanted 15-minute time steps, that would be a monumental pain in the choose your body part du jour to do that graphically. Because you'd have to photo enhance it a lot, go to one of those big old Kinko printer thingies that's wider than my wingspan, just so you could draw the stuff at 15 minutes. Dumb way to do it. That curve is tabulated in the report. You pull the tabulation and you can simply do the calculations in a computer spreadsheet, or God forbid, in your hand calculator. And this is now rescaled from 0 to 3 hours, 0 to 2.6 inches, and lo and behold, it has the same shape as the curve in the report because it's supposed to. I think it's far easier to use the tabulation. In fact, I thought it was so much easier. Another grad student, colleague of yours, who has the fluid mechanics laboratory right now? Okay, who's got the blonde girl named Caroline teaching it? Okay, she did this. This is her work. So curse her if it doesn't work for you, but congratulate her on a job well done. Okay, so she built a tool that all you have to supply is the depth, duration, and the desired time increments, and it will return the time series of cumulative depth. And its purpose in life is so you could copy and paste directly into Heck HMS. 3 minutes to go, and you'll be out of here. Assuming I can find it. Okay, so here's the Texas hyetograph for the 50th percentile storm. What was our total depth for that 3 hours? I think it was 2.6. So you would enter 2.6 inches right here. You got the 3 hours, the total depth, and let's say we want to know what the cumulative depth is every 10 minutes. This is rough.